Okay, hello AP Physics. The reason I'm sending out this new video, which I'm just making right now from home, is because you have your notes on simple harmonic motion. You have the first example of simple harmonic motion. You should have looked through both of those at this point. It's Wednesday morning. There was one in-person tutorial that I did not make a video for because usually I just plan on doing this one in class. However, it's obviously impossible right now, so I do want to show you this tutorial because this might help with some of your work on oscillations. So the issue here, and those of you who went to Darien Lake, you'll maybe recognize this ride, very common at theme parks, the pirate ship ride or the Viking ride or whatever you want to call it. An amusement park ride designer is researching the pirate ship ride to put at his park. In reading the description of the ride, he realizes that he can essentially treat it as if it were a simple pendulum, meaning all of the mass of the ride is concentrated at the bob or end of the pendulum, with the support being rigid and massless. So that means that in this picture right here, this is where all the mass is concentrated, which is not exactly true, but it's good enough for us doing a few calculations here. You can treat this as a pendulum that swings back and forth with an anchor point up here. If the distance from the ship to the pivot about which it swings is 15 meters, what is the period of the pirate ship's oscillation if timing is started when the ship is motionless and displaced 20 degrees from its equilibrium position? Assume no friction and that the motor for the ride, is turned off. So that means equilibrium would be when it's hanging straight down 20 degrees, maybe about this much up. So we want to know the period of this. Now, if you remember from the notes, this was an equation that I did not give you, okay? Because the idea was that we wanted to look at this, we wanted to actually do this in class and figure out what the equation should be. Obviously, that's going to be kind of hard to do right now. You could actually try this at home. It's very easy to verify that the period is given by the equation which I sent out in the remind and which I'm about to show you. You could do that at home. That would be actually kind of interesting for you to try and set up. If anyone does that, send it to me. Might consider that for some sort of credit. But in any case, the equation for the period of a pendulum is as follows. TP, so period of a pendulum, is equal to 2 pi times the square root of L, that's an L, over G. 2 pi times the square root of L over G. This is very easy to plug in for. This is like Regents level stuff to plug in for. 2 pi, we know that the length of the pendulum is 15 meters. And we can approximate G, as we have all year, as 10 meters per second squared. And we come up with a period. Let me do my calculations. So let's see, we got 15 divided by 10. I didn't even need a calculator for that. That's 1.5. I'm going to take the square root of that, and I'm going to multiply by 2 and multiply by pi. And you see that I get 7.7 approximately seconds. 7.7 seconds. Okay, so what that means is it takes 7.7 seconds for the pirate ship to swing from 20 degrees up through equilibrium up to here, and then back through equilibrium and to where it started. That is one period. A period is not just going from here to here. Okay, that's half a period. A period is the time it takes to get back to where it started. How is the usefulness of the equation you used above limited? So this is kind of tricky. When we talk about simple harmonic motion, I believe this was mentioned in previous notes. When we talk about simple harmonic motion, for an object on a spring oscillating back and forth, a mass on a spring, there is no limiting factor. The period equation will always work. Simple harmonic motion is the right way to analyze that. For a pendulum, it is usually the right way to analyze it unless the swing of the pirate ship gets really, really big. Okay? And so the answer to this question, this is just something I want you to be aware of, this equation only works for what is called the small angle approximation. Okay, and you might remember that from our notes. And small angle approximation means that this equation is no longer very accurate for maximum angles of displacement over about 30 degrees. So if you're displacing this up 35 degrees, 40 degrees, and you're expecting this equation to give you a realistic period for a pendulum, that's not going to happen. And then this is the equation that it really matters for, the period of the pendulum. That's where this small angle approximation matters. If you do want a quick review on small angle approximation, it's essentially the idea that, I'm trying to think of what it is. It's the idea that I don't want to say the wrong thing. It's on my other set of notes. It's the idea that when you take the sine of theta, so let's say I take sine of 30, and it becomes 0.5. If you were to do 30 degree, I think this is how it works. If you do 30 degrees in radians, let's see, so that's pi divided by, pi divided by 6. Okay, so yeah, that's what it is. Sorry for the delay. The small angle approximation says that if you, it essentially is the regime where sine of theta is approximately equal to theta, and this is in radians. Okay, so when the sine of theta, so sine of, well, so this is in radians, sorry. 30 degrees, the sine of that is 0.5. 30 degrees in radians is pi divided by 6, 0.52. It's approximately the same thing. The idea is that this equation is an approximation. It's a much simpler equation than, I guess, what you would call the actual equation for the period. It's close enough so that it's useful to use. However, if we were to do, let's say, the sine of 45, okay, 0.707. If I were to do pi divided by 4, okay, so that is starting to get, it's at least like a tenth away. This is where it starts to, cause more problems. If I were to do, obviously, the sine of 90, 90 sine is 1, and 90, let's see, that's pi over 2. If I do pi divided by 2, okay, that's very clearly not very close to 1 anymore in the grand scheme of things. So that's what the small angle approximation is. You don't need to know all the rules behind it, but you do need to know that this equation for pendulums only works if you're using an angle of under approximately 30 degrees. All right, list and explain two different possible methods for decreasing the pendulum's period. Well, let's just look at our equation. How could we decrease the period? Obviously, you're not doing anything to the 2 or the pi, so that doesn't work. The only things you can do, I guess you could do a third thing, depending on if you're still using small angle approximation, but the two that I'm most concerned with are somehow changing L or changing G. If we want to decrease the period, we definitely should decrease L. It's on the top of this fraction. If you decrease L, this fraction and the square root that's around it will go down. Multiplying by 2 pi is still going to be smaller than it was before. So you could decrease the length. And what are you decreasing the length of? I would say probably these supports here, okay, of the supports for the ship. Thereby shortening the length of the pendulum, since, I'm just going to write the equation again, Tp equals 2 pi square root of L over G, and doing this would decrease Tp. The other option, well, the second option I should say, is somehow we could change G. If we wanted to change G to make this smaller, we wouldn't decrease G. That would make this fraction, the denominator, that would make the denominator bigger, or no, smaller, which would make the fraction bigger and make this bigger. Instead, we want to increase G. So you could also find a location with a higher acceleration due to gravity g. Oh, and by the way, the length, I'm going to sneak this in here, is L. Which would also decrease the pendulum's period. Now, where would you find a location with a higher acceleration due to gravity? I would say you could probably find a location like that, maybe closer to the center of Earth. And how could you get closer to the center of Earth while staying on the Earth's surface? Go to a location maybe lower, like closer to sea level or even below sea level. Death Valley, for instance. So this could be found where Earth's surface is closer to its center. Now that's a pretty full and complete answer. I explained exactly how to change the period of the pendulum, and I even showed why. So I even used the equation, I used the variables that are given in the equation. You should be starting to answer questions like this in preparation for the AP exam. Okay? There's nothing anyone can argue with in here. If you just say decrease the period, or decrease the length and increase g, then that's kind of like, okay, well, can you prove that? What is your reasoning for saying that? You always state your answer, defend your answer. The only other thing I could think of is possibly, well, no, I don't want to get into the small angle approximation, so we'll leave that out. All right, so fairly simple to start off. In order to get the pirate ship up to higher heights, a motor is used. Typically, the motor is off during the downward motion of the ship and on during its upward motion. You become interested in knowing the speed of the ship at the bottom of its motion and how that is related to the angle that it swings down.